All right. The third quantum number is magnetic. Okay? M subscript L. Okay? That's the magnetic quantum number. That defines the orientation. Right? Orientation is just direction of individual orbitals within a subshell. So the subshells were that letter number combination we were talking about. 1s, 2s, 2p, 3s, 3p, 3d, and so on. Okay? So we're going to have multiple copies of an orbital, okay, possibly within particular groupings, like we called those subshells. Okay? So here are the possible values for m sub l. It's only integers from negative L to positive L. So it determines on what value of L we're talking about. And remember, L was the shape, right? So we can only go from negative L to positive L. So let's start with n equals 1. Okay? L can only be 0. That's 1s. Okay? That's spherical. Okay? For magnetic, we can only go negative 0 to positive 0, which is just 0. Okay? Which means we have only one orbital. Okay? That's it. That's really because spheres have no orientation. If something is a perfect sphere, okay, rotating it doesn't change that sphere. Okay? So magnetic quantum number, really we're talking about orientation. So there's only one sphere, okay, 1s, that's it. And there are no copies of it with different orientation because it's a sphere. Okay? So same with 2s. Okay? Spheres have no orientation, only one orbital. Okay? But now in 2p, okay, L equals 1. Those are p's. Okay? So our possible values for the magnetic quantum number are negative L to positive L. Okay? So negative 1, 0, and positive 1 tell us that there are 3 orbitals. Okay? And I've got models of those 3 orbitals right here. Okay. They follow the same. They follow the 3 coordinate axes of a 3-dimensional system, right? One would be sort of on the x-axis, one would be on the y-axis, and one would be on the z-axis. Okay. They're all occupying the same space, so you know it would be sort of like that. You know, but we've just got them separated there so you can see them. So every 2p subshell, okay, is made up of 3 of these orbitals. Okay? And sometimes they're called px, py, and pz. Okay? But that's because we're at L equals 1. So we got negative 1, 0, and positive 1 for our 3 orientations of that. Okay? So it's pretty nifty. So 3, just on the last page, we can do like we did. We can go 3, 0, 3, 1, and 3, 2, which is 3s, 3p, 3d. Again, with the sphere, there's only one orientation of a sphere. Right? Okay. With p, that's negative 1, 0, and 1. And there are 3 of those, just like 2p. There's 3px, 3py, and 3pz. Okay. How many different orbitals would there be in this group of d orbitals? Yeah, it's going to be L equals 2. So we're going to go negative 2, negative 1, 0, 1, and 2. There are 5 orbitals. In any d subshell, including 3D. I'm going to show you pictures of them here in a second. Okay? Let's do the 4s also. 4, 0, 4, 1, 4, 2, and 4, 3. 4s, 4p, 4d, and 4f. Okay? 0, that's it. Just one of them. Negative 1 to positive 1. There's 3 of those. Negative 2 to positive 2. There's 5 of those. Okay. How many f orbitals are there in any F subshell? Yeah, we got -3. Okay, there are 7 orbitals in F subshell. Okay, so we can fill out our little table right here. Okay, we get a nice pattern going that for every S subshell, there's just one orbital. Okay, because there's only one sphere that can occupy a certain place, no matter how you rotate it, just one sphere. Okay. When you have something with 2 lobes like this, in order to make this spherically symmetrical in all, you need 3 of them. You need one on the x-axis, one on the y-axis, one on the z-axis, turns out. Okay. We need 5 of these, we need 7 of these. And this all sort of comes from mathematics. Mathematics predicted this behavior actually long before it was verified by experiment, just due to the symmetry of cutting things in half 3-dimensionally. Okay? If we start with a sphere but then cut it in half, we have to have 3 of those things in order for it to be symmetrical. When we start cutting things twice, you need 5 of those in order to make it symmetrical. When you start cutting things 3 times, you end up needing 7 of them to make the sum of that whole thing symmetrical, it turns out. Okay? So combined together, the principal number, the angular momentum number, and the magnetic number all together define a particular orbital. Okay? Remember, we said an orbital is a region where you could find an electron. So let's say, let's review one more time. What does N specify? Size and energy. Just energy. Okay? What does L define then? Shape. L defines shape. With a slight change in energy. But N is the primary determiner of energy. Okay? And then what did we say M sub L determines? Orientation, correct. The group of orbitals within a subshell, like px, py, and pz, they all have the same energy. Okay? So let's actually write here all the same energy. That's important. Okay. So this one and this one and this one all have equal energies to them because there is no real up or down inside of an atom, right? They're tumbling whichever direction. So there is no real difference between px, py, and pz other than the fact that within any atom you have this group of 3 orbitals that together look like that. Okay? So, but they all have the same energy because they're only different by what direction they happen to be pointing. Okay? So I just got some pictures here that'll hopefully reinforce what we just talked about. Every S subshell has a single spherical orbital, okay, because you can't change the direction of a sphere. Every P subshell has 3 dual lobed orbitals. We got Px, Py, and Pz. Okay? These 3 are all in the same area. Okay? We always draw them next to each other so you can see them. Okay? But if we drew them all together, I mean, I could draw them 3 different colors, I suppose. There's 1. There's 2. Let's try that one again. Okay. There's 3 going forward and back. Okay. And all together, this is a P subshell containing 3 orbitals. Okay. Px, Py, Pz. Just sort of the 3 axes of the coordinate plane. Okay. Here are pictures of the 5 d orbitals in a d subshell. Okay. You have 3 of them that you would sort of expect okay, that have their two nodes along two of the coordinate axes. Okay, so yz, dyz has a node along y and a node along z. dxy has nodes along x and y. dxz has nodes along x and z, as you would expect. Okay. There's one more then that has, this is called x squared minus y squared. It has to do with the coordinate systems. There's some algebra there, something like that. The difference here is that we've got nodes in between two of the axes. Okay. So you see these lobes are right on the x-axis and the y-axis, it turns out. Okay. That's one of them. And then my favorite one is this one over here. It's got two lobes up and down, and then sort of a hula hoop around the middle for some reason. But that ends up being symmetrical with this one right here in order to make the whole thing symmetrical. So it doesn't make it. I don't entirely get where that little hula hoop comes from, but like I said, these were predicted by math long before we actually verified that this is where electrons are. And if you want to have something with, if you want to have a group of things with two nodes to them that overall end up being completely symmetrical when you average them all together, this is how you do it, and it's kind of interesting. Right before we go, let's see if we know these rules for possible quantum number sets. Because this is a very common question that's asked. You know, if you're given several sets of quantum numbers, which one is valid or which one is invalid? Because there are certain sets of quantum numbers that are impossible. Okay, so let's say we had here. Let's just make a little table here: n, l, and ml. Question. Okay, so let's say 5, 3, and 2. Is that valid? And if so, what would we call it? So rules of n. N is an integer. N can start at what? What's the first n? 1. Okay, so n is totally fine. Okay. L also an integer. L starts at 0, but what's the max L? N minus 1. So we're good. The max L here would be 4. Okay, so we're good there. Okay. And ML goes from what to what? Negative L to positive L. Okay, so this is okay, right? We would call this a 5 what? What letter would we give that? D, right? L goes 0, 1, 2, 3, right? So is it D? Zero, 1, 2, 3, S, P, D, F. Okay. Don't forget, L starts with 0. S, P, D, F. Okay. So what would this be? 5. This would be a 5F orbital. Okay. What about 2, 1, 3? Is that a good-looking group of quantum numbers? No. What's the problem? My magnetic number is beyond the bounds of -1 to +1. Okay. 2, 1, 1 would be okay. What would we call that? Yep. And since ML can go -1, 0, +1, okay, that would sort of be the third of that group of 3. Okay. So don't forget, L starts at 0. That's what everybody forgets. So, all right. So we're not meeting on Wednesday because there's no class, right? Work on your mastering chemistry. That's due Sunday night.